is draw this closure. So we want to evaluate the Laplace transform of the hyperbolic cosine of bt. Is anyone familiar with hyperbolic functions? Oh, that's a shame. That's a shame you couldn't teach this. The hyperbolic functions are essentially just the trig functions, but it's only real values. And cosine, remember, is e to the ix plus e to the minus ix all over 2. Cosh is just e to the x plus e to the minus x over 2. We're going to use that to find this transformation. But remember that the Laplace transform is linear. What's the transform of e to the bt?
One over s minus b.
What would the transform of e to the minus bt be then?
1 over s plus b.
And let's now simplify that. Raise a single fraction. Going to be left with 2s in the numerator, right? Oh, 2 over 2, that's gone. The numerator is just going to be s. If you look at the denominator, isn't that difference squares? There's your Laplace transform. S over s squared minus b squared. Now we'll just evaluate, what is it, 3 1? These 3. we're going to use the first shifting theorem. Okay. Right, big F is the Laplace transform. So let's start with that one. First thing we want is the Laplace transform of t. What did we say that was?
One over s squared.
First shifting theorem says that's just going to be big F of s minus a. So replace s with s minus a, and there's your transform. Where we say the transform of sine omega t was?
Omega over s squared plus omega squared.
Then Laplace transform of interest is big F of s minus lambda. And there's our Laplace transform. And what is the transform of cosine omega t?
S over s squared plus omega squared.
And that, again, call it big F of s. Then our Laplace transform is big F of s minus lambda. And so maybe that's one of the theorems you write down on the green sheet as your first shifting theorem. So if you ever take the Laplace transform of the exponential function times something, that generally tells you it's the first shifting theorem. Find the Laplace transform of f of t first, then replace s with s minus whatever the coefficient of the power is. Questions on the Laplace transform? And so last meeting we used the definition, right? Which was terrible integration. Actually, the integrals we did weren't that bad. Fairly tame. Imagine trying to do one of these by hand. They're still fairly tame, but worse. Next class, I will post the table. I'll upload the table. I also want to cover inverse Laplace transform before I actually post it. And then today we kind of not did the integrals, and unless you're specified otherwise, you don't have to use the definition. You can just use the table and the appropriate theorem. That's what we just finished. So I think what I'm going to do is push everything back. And so if I do that, this we can just ignore. Let's go and straighten that out. I'll try, what I might do is, instead of doing two worksheets for these, I might just combine them into one. And try to give at least 75 minutes for that review. So that's what I'm aiming for. The quiz was originally scheduled to be due on the 12th. It covers everything up through that lesson. I'll make that due the 14th instead. And then no changes to anything, which I just wrote. So that's the goal. Hopefully we get no more school closures. That would be nice if we didn't do that. Oh, gee, that's actually like 45 minutes. Let's begin the groups. The inverse Laplace transform is undoing. In other words, you're given big F of S, the inverse Laplace transform finds the original function. Inverse Laplace transform is linear as well. That property is extremely useful. Also, I hope you remember your partial fraction decomposition, because that is also going to be used a lot. Remember that from Calc 2, which is actually just an algebra technique. Uh-oh, you don't? Well, I'm about to make your day. You don't need to know. Someone's going to do it on the calculator. I will show you both. I'll show you both Wolfram and T inspire. So that's going to save a lot of time. And again, I would recommend you take advantage of that for the exam. If you try to do it by hand, you probably won't have the time.
So this is the
Yeah, it's homogeneous systems up through the end of the semester. So basically all calculator, finding eigenvalues and eigenvectors, and then this fun stuff. Actually, you can also find Laplace transforms and inverse Laplace transforms for you, but that you're not allowed to use. Here's the general idea. These are simple. What you first want to do, look at 1 over s squared minus 1. What function had that as a Laplace transform? And of course, you will have a table when you really need it, so you can look it up.
Cosine? Is it cosine?
It's not cosine.
To the T. It's negative.
This one should be sine. Cosine's with s in the numerator.
Oh, right.
Right, so doesn't this kind of look like k over s squared minus k squared? Which is sine of kt. What's k? What would k be?
-1.
It's just 1, right? So the transform of sine of t is 1 over s squared minus 1. So the inverse transform of 1 over s squared minus 1 is just sine of t. And you don't need to write that first part. I'm just explaining how to get into it. So on the exam, you could just write the inverse of sine of t. Because it's very unlikely you'll get one that simple on the exam. Nice, but not that nice. Which of the known Laplace transforms does s over s squared plus 9 fit? Right, so what values do you need for cosine?
9.
So it's s over s squared plus
Oh, 3.
omega squared, right? So omega is 3?
Yes.
So our inverse transform is just cosine of 3 theta. Use the linearity properties. That first inverse transform, what form does that look like? 1 over s plus 5 looks like it's going to be the transform of what?
E to the AT,
What is a?
negative 5.
That first one, just be 8 e to the negative 5t, right? Look at that second inverse transform. 1 over s squared plus 3. What does that resemble?
Sine.
It's going to resemble a sine. What's the problem?
It's not squared.
Well, it is squared. So what would omega be?
Root 3.
So what's the problem? What's the transform sine of omega t? Is it 1 over s squared plus omega squared? What is it?
Omega over.
What's the problem?
The root.
We don't have root 3 in the numerator, do we? There's 2 things you're always allowed to do in math. Add 0, multiply 1. But it's linear. So we can factor out that 1 over root 3. Ah, now that inverse transform matches sine. And there's your inverse transform.
So what allowed you to do the root 3 over 3 in the numerator?
Isn't root 3 over 3 1?
It is.
Yeah, anything divided by itself is 1, isn't it?
I guess I just don't recognize root 3 over 3 as well.
I'm sorry, root 3 over root 3 is what I think I wrote.
Oh. It was root 3 over 3.
It should have been root 3 over root 3. Yeah.
So then you, oh, I see what you did. Okay.
And then, because it's linear, I can just pull out the 1 over root 3. So I will skip that intermediate step. Right? If I need to multiply the numerator by a constant, I'll just divide outside by the same constant.
I see.
It's the same as multiplying by 1. Guess you could go out. This one will not require partial fraction decomposition. But if you don't know that off the bat, you want to try it.
How would you do that? Just by,
Sorry, the word.
oh,
I'm saying if you don't, I'm not going to show you how you would know. It was 3s plus 8 over plus 2s plus 5. That's right. You don't have to define the function first. I just prefer it so I don't have to write the fraction more than once. Menu. Algebra. Should be fraction tools. Get numerator. Or I think you can actually do, no, that's proper fraction, something different. Get numerator. Oh, that's okay. I think that's it. One complete square. It might actually be factor. That was complex. I won't complex. I think it is. I think it's factor. I wonder if I know it's going to require it. No, that's not it. Wrong. It's the opposite. It's expand. Expand, not factor. Did the opposite one. So what you would do is take your function, go expand f of t, and it's going to give you the exact same thing. Right, just as two separate fractions. Which means it's already in its partial fraction decomposition form. It can't be simplified any further.
So you declare f of t, do get num, and then expand.
Yeah, so you don't actually have to declare your function first, if you don't have to write fractions more than once. Although, with this case, I'm not going to have to. So you could just do expand, and then within your fraction. Well, that's just the same thing. So obviously, partial fraction decomposition is not going to work here. Which means there's one other method to try. It's one of the most common methods. You used it a lot in algebra. Take a guess.
Complete the square.
Completing the square. Complete the square of the denominator. Which, if you noticed, there actually was a command in your calculator to complete the square. It's fairly simple to do anyway, so I'm not going to use it, but it is there. We want s squared plus 2s plus 1, don't we? Well, isn't 5 1 plus 4? There you go. There's what your complete square will look like. S plus 1 squared plus 4. So now we're going to have to do what my favorite professor calls dark voodoo algebra. Because it's not intuitive at all. We have an s in the numerator, right? But we have an s plus 1 squared in the denominator. Which means I'm going to want s plus 1 in the numerator. Because of the first shifting theorem. Isn't 8 3 plus 5? So 3s plus 3 plus 5. Now what we're going to do is split this. Right there. That's two separate fractions. Notice we can factor out a 3. There's the first. Factor out the 5. If you replace s plus 1 with just s, a little bit easier to replace it. What does that look like? S over s squared plus 4.
Cosine?
Cosine of what?
2.
Cosine of 2t, right? But it's not s. It's s plus 1. But that's the first shifting theorem. So it's just going to be e to the negative t times cosine of 2t. Or 2t, rather. Look at that second. And again, for now, just imagine s plus 1 is just s. 1 over s squared plus 4 looks like what?
Sine
Sine of what?
2t.
But what's the problem? Because it isn't actually sine of 2t.
Of the 1 in the numerator, so we have to do the same thing.
What does that 1 have to be?
2.
Now it's sine of 2t, right? But that's an s plus 1, not an s. For shifting theorem. It would be s to the 2t, then just multiplied by e to the negative t. And there's your inverse transform. Right. The inverse transform itself isn't really that difficult. You just have to recognize, well, what form does it look like? It's the algebra. That's going to be a pain.
So why is it e to the negative t and not e to the negative 2t?
Because it's s plus 1. For the first shifting theorem, you just look at what is s being replaced with. Right? It gets replaced with s minus a. So it becomes e to the at times whatever it would be if it was just s. Right? In this case, a is negative 1. Right? So the first shifting theorem actually technically has 2 parts. It has one for the Laplace transform and then one for the inverse Laplace transform. But they kind of just go together. And if I remember correctly, I don't think your book calls it that, but the second shifting theorem I think has to do with the unit step function, which we won't cover for a couple classes. But I think that Laplace transform is called the second shifting theorem. Right, so this is actually the example I used to determine if it was factor or stand. So you saw how to do it on calculator. I'm going to show you how to do it on Wolfram now. Very easy. The command you want is apart. And then just type in the fraction. And there's your decomposition. Again, if it doesn't have a decomposition, so I'm just going to show you what it does here. It just gives you the same fraction. And that's how you would know, well, that's not going to work, so maybe try complete the square. So here's our decomposition. You have to, one of the quirks with Wolfram's pi, the only thing I don't like about Wolfram is it likes to write it in ascending order of powers and not descending order of powers, which to me just looks wonky. So I just adjust that. But there's our decomposition. 8 over s minus 2 minus 5 over s minus 1. Without having to do that nasty algebra. Right? And it is, again, linear, so now you just use your linearity properties. What is that first inverse transform?
You need to do that T.
What about the second one?
T.
There's your inverse transform. Bet you wish you knew this in Calc 2. It would have made that integration a lot easier. By the way, I actually allowed in my Calc 2. I don't test them on that algebra anymore. That's already been tested. Can't even use it. That's all I care about. Of course, back in my day, we weren't allowed to calculate at all, so when I took this course, I had to do all this by hand. We were allowed basic calculations. It's like $300. Yeah, this one just looks hideous. Which is why calculator. Oh, this is definitely partial fraction decomposition. Right now, granted, even if you reduce by hand, it is still fairly simple because it's just 4 linear factors. Right? The a over s plus b over s minus 1 plus c over s minus 2 plus d over s plus 1. And that is really simple to find a, b, c, and d. We don't have time for that. So first, try and do it in your calculator. make sure that's what you get. And notice how I wrote it out. I put it so that the constant is in the numerator. That's why I wrote it as a compound fraction. Use linearity properties now. Now go turn by turn. What is that first inverse Laplace transform?
E to the 2t.
What about the second one?
E to the t.
What's the third one?
T.
It's just one. And what about that last one?
E to the negative t.
And there's your transform, or there's your inverse transform. And remember, since this is all addition, the order doesn't matter. So again, go ahead and find that decomposition in your calculator. Yeah.
Negative 6 over s plus 2 minus 8 over s plus 2 squared plus 2 over s plus 1.
Good. No problems, just don't forget how you did that. In time for the exam, right? And also make sure your calculator's charged over the suck. So that's what it is. And I'm going to write it in a different order than what's presented for a specific reason. And there's the order I'm going to use. Use your linearity properties. That first transform is what?
2 e to the negative t.
What about the second one?
Negative 6 e to the negative 2t.
Now, for that third one. Well, that doesn't match anything that we've seen so far. But, what if that s plus 2 was just an s instead? Is there a function that has a Laplace transform of 1 over s squared? What is it?
T.
This is a first shifting theorem problem. So you're going to have t times e to the what? Minus 2 what? Minus 2t. There's your inverse transform. So generally speaking, if it's s minus a, you should think first shifting theorem. Because you could argue that even the 1 over s plus 1, you can use the first shifting theorem. What's the inverse transform of just 1 over s?
E to the s.
1.
It's just 1 times e to the negative t by first shifting theorem. So that would just be a general rule of thumb. It's s plus something, s minus something. Think of it as just s and then use first shifting theorem. Again, more practice for finding the decomposition. Yeah, it's good to get this in now, not to worry about it on the exam. is it?
1 over s plus 2 minus 9 over s plus 2 squared plus 21 over s plus 2 cubed.
Again, for this, Wolfram likes to do the denominators in ascending order when it should be, or descending order when it should be ascending order, but whatever. What is that first transform?
Either negative 2t.
Second transform should be used in the first shifting theorem. What's 1 over s squared inverse transform?
T.
So we should get as an inverse transform what?
9t e to the negative 2t.
Now that third one. 1 over s cubed. What is the inverse transform of 1 over s cubed?
T squared.
You're close. It fits t squared, but it's not exact. So go back. Oh, did we do the transform of t squared? Yeah, it was on the worksheet. What is the transform of t squared?
2 over s cubed.
2 over s cubed, right? Specifically, it's actually rather painful to prove, but for any positive integer, transform of t to the n is n factorial over s to the n plus 1. And again, that'll be on that table. So you want 2 factorial over s cubed. There's not a 2 there. What were you going to say?
Well, I was just confused how you got negative, or I know you got the minus, but the 9te negative 2t,
So what's the inverse transform of 1 over s squared?
1 over s squared, e to the negative. Oh, you put in, okay, so you did the s plus 2 equal s, and
Yeah, just imagine it as an s, and then you go, okay, what function transforms to 1 over s squared? That's t.
and the minus 2t is
First shifting theorem then tells you multiply that by e to the negative 2t. So it's s plus 2. We need a 2 in the numerator, so we're going to wind up dividing by 2. That transfer would actually be t squared over 2 if it was just s cubed. Now, first shifting theorem. And there's your inverse transform. So in general, if you think of the inverse transform of 1 over s, I think they do in those tables s to the n plus 1, not s to the n. Like they write it's 1 over s to the n plus 1. It is t to the n over n factorial.
you divide by 2, multiply by 2 again? Why do you divide by 2 on the 21 and multiply by 2?
Because the transform of t squared is 2 over s cubed.
Oh, okay, so you get
So I'm going to write 1 as 2 over 2 and factor out the 1/2.
Since you know that we use the table provided.
There'll be a table provided, yeah. It won't give you t squared, it'll give you t to the n. That's n factorial over s to the n plus 1. That's actually proved using the gamma function.
Can we see the table you provide us before the exam?
It'll be given with the exam, and then I'll also upload it on the SharePoint. So again, it's one of those things where you don't have to worry about bringing it with you. It will be provided. There was also a table in your book, but that's not the table I'll be providing. Section 8.8, I believe, is the table of transforms. So notice I just wrote the denominator in its completed square form. Right, this way. Right, so let's say the problem didn't already given completed square form, right? You got this as your output for the partial fraction decomposition. That second fraction should tell you that you're going to need to complete the square in that denominator. And thankfully, it was already done for us. Well, that first transform is really simple, isn't it? What's the inverse transform of 1 over s?
T.
1.
Just 1. Well, now we need to look at that second one. S plus 1 quantity squared, which means I want an s plus 1 in the numerator as well. So 7 plus 5, right? What is that first inverse transform?
Cosine t and negative t.
What about the second transform?
Negative 5 halves and negative t sine t.
Here's your inverse transform.
How can you recognize the split up the fraction like you did with 7 halves and 5 halves?
Which part here?
Yes.
Well, I want s plus 1, so the s plus 1 there. So I'm factoring out 7. And then I factor out 5, right? So I'm splitting it right here. So I can have an s plus 1 in the numerator.
And you took out the 1 half. Where did that one come from?
This one,
Yes.
I just factored out the 1 half. And so this is the same as 1 half times 12 plus 7s.
Oh, I see.
So I just factored out the 1 half.
Okay. Got it.
So this time I will write the 3 in the denominator. Then linearity. Allows us to write this. But now, each of those can be split further, right? Split this way, wouldn't it? Once you factor out the constants. What is that first inverse transform?
Cosine T.
What's the second transform?
Eight over 6 sine 2t. Eight over 3 cosine.
8 over 3 times what?
Cosine.
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 What is that third transform?
Eight over 6 sine 2t.
Negative cosine.
Third.
Minus 1/2.
Negative cosine 2t.
It's just negative cosine 2t. And cosine is just s over s squared plus k squared. What about that fourth one?
Four over 3 sine 2t.
And there's the inverse transform. there any questions on the inverse Laplace transform? We now have all of the tools necessary to start solving initial value problems using the Laplace transform, which is what we do next. I'm not going to change that. I'm not going to change the initial posting date. I'll just change the due date. And so the final quiz should be quiz number 5, right? That'll post after next class, which is when I was originally supposed to post. But it will be due on August 14th before the exam start time. It is Jack's job to remind me to change the due date. So if I don't, it's his fault,
What if I just,
and everyone will fail.
what if I just text you about it right
But I hope I remember to check my messages.
now? I'll just like spam you messages every 5 minutes.
All right, don't forget to continue working on that green reference sheet. Final group assignment. As of right now, still set to be due next Tuesday. I may also change that to Thursday as well.
Is the exam the final last class, like the entire class?
It won't be the entire 125 minutes. It's only going to be 2 hours. So it'll go 1 to 3.
And some kind of assignments commission.
Maybe. So aim for it to be due on the 12th. I have to, let me just look at it now. Do I need convolution for it? Oh, it does. Crap. It's even step function. Let's change that as well. To be doing the 14th. Because you do need to use the unit step function, which I'm not going to cover probably until the 12th. Next class, what we're going to do, so on Thursday, you'll have the first 30 minutes to work on the inverse transforms worksheet. 5-minute break, and then we're going to do 2 sections. We're going to do solving initial value problems and also convolution. I'll define what convolution is, which would allow us to solve what's called integral equations. And then next Tuesday, lots to go, and then I'm going to try and fit in the unit step function as well. With that, remember the last worksheet will just be all of that together. And then you have the review worksheet next Tuesday. Worst case scenario, I just gave you the review worksheet to take home. I post the solutions. That's the
That-
worst case scenario.
That worksheet,
It won't count as part of participation. I'll just post it. I'll just upload it onto SharePoint.
but
for you
will
to
it,
go over.
will it mimic what's on the,
It'll be the same as what it was for the first two exams.
so just like,
Yeah.
great.
So worst case scenario, I just won't do that as participation. I'll post it right online for you to go over. So we'll see. We'll play it by ear. See, for a second.